So the first thing we want to do is try to make sure that we have a firm grasp of what the central limit theorem is saying. And it's important because the central limit theorem kind of looks, abstract and mathematical, and there is a little bit of that, but nevertheless, the central limit theorem is actually a very concrete statement, and it really is nothing more than a precise way of describing what we were talking way back in chapter 3 about, which was the scatter of the estimators. Now, in the review video I did earlier, I've already covered all of this, so I'm not going to spend a lot of time talking about this, except just to point out a few helpful hints that you might want to think about when you're working these problems. The first is, when you're working these problems, you definitely want to try to use what we learned in chapter 2 about context. So if I was reading these problems, first I determined the parameter, then the variable, then the population. And you also want to make sure that the assumptions are satisfied before you use the central limit theorem. If they aren't, you can't do the problem, okay? So I want to take a look at a few of these problems, and let's kind of work through them. I'd like you to stop the video and read the first problem, please. Okay, so the first thing we want to do is we want to get a handle on the context. And so first I want to identify what the parameter is. And when I'm reading this, what I'm looking for to identify the parameter is either an average or a percentage, right? And in this case, as I'm reading it, I come across the word average. So I know that I'm probably going to be working with the population mean. So the next thing we want to do is we want to figure out what is the variable mean of what, right? And one of the nice things about starting with the parameter first is that the variable generally comes right afterwards, right? Average of what? Average of weight of loaves. So this tells us that our variable is the weight of a loaf of bread. Okay? And so what is our population? Well, when we read through this, we see that we're talking about the loaves that some baker makes, so it seems safe to say that the population is all the loaves made by the baker. And now that lets us put a little finer point on what the parameter is. So mu is going to be the average weight of all the loaves of bread made by the baker. Or we'll say the average weight of all the loaves made by the baker. Let's try to get, there we go. Okay, good. Now what I want to do is I want to try to figure out what all these numbers mean. I'm going to try to take the problem apart here. And so if I look at the various numbers in this problem, right, let's see. I see 12, 16, and 0.5. And so if I look at 12, I can tell that this is going to be the sample size. Right, we take a sample of 12 randomly chosen loaves. So here, n, the sample size is 12. For the 16, we say if the average weight of the loaves were 16 ounces. Now, when you're dealing with averages, you have to realize that there's two averages going on in the problem, right? There's going to be a population average, and there's going to be a sample average. And how do we know which is which? Well, if we have a sample average, there has to be some sort of language telling us that this average was computed from a sample. If it's a population average, it's going to just be stated as a fact. So here we say if the average weight of the loaves were 16 ounces. Notice that there's no reference to a sample and it's stated as a fact. So here, this is a population average, so we know that mu is equal to 12. And by the same token, the standard deviation, again, there's no mention that it comes from a sample and it's stated as a fact. So the standard deviation, sigma, is equal to 0.5. And I won't bother to put the units, okay? Now we have everything to apply the central limit theorem. So first of all, let's check our assumptions. Do we have a random sample? Right. Let's go back to the assumptions for a quantitative variable. Is our sample random? Yes. We're told that we have 12 randomly chosen loaves. So random is okay. What about the sample size? So we notice that we either have to have a sample size greater than 30 or the variable has to have a normal distribution. And we don't have a sample size of 30, we have a sample size of 12. So the only way we're going to be able to use the central limit theorem is if our variable, the weight of the loaves of the bread, okay, has a normal distribution. And if we go back and we look at the three general things that we can assume have a normal distribution, standardized test scores, physiological measurements, or deviations from a manufacturer's claim, we see that this falls under deviations from manufacturer's claim. So yes, it's normal. And is it too large? Well, we have a sample size of 12. The baker would only have to make 120 loaves total for this to be too small, and that seems unlikely. So our assumptions are all okay. So now we can use the central limit theorem. So the central limit theorem is answering this question, right? What would the distribution of the sample averages, the mu hats, be? And so the central limit theorem tells us that mu hat has a normal distribution. And I'm just going to go up here and put the numbers in, right? I'm going to put whatever the value of mu, sigma, and n is. So mu was 12, sigma was 0.5, and n was 12. So it's 0.5 divided by the square root of 12. And if we compute 0.5 divided by the square root of 12, we're going to find out that's about, let's see, 425 square root of 3 is 1.7. It's about 0.145 roughly. So it's going to be about 0.145, I believe. Let me just check really quick. Doing it in your head, you can make mistakes. Let's see. We don't use calculators very much in this class. Actually, it's 0.144 is a little off. But this is one situation where you could, or you can do this in Excel. Okay, so this is what sample averages should look like from his population. Okay, actually this was 16. I don't know why I said 12. I apologize. Sorry for the confusion there. Yeah, I was messing up the sample size with the population mean. Sorry. Right, this is mu, and our mu is 16. Okay, and that's our final answer. Okay, I'd like you to stop the video and read problem 2. Okay, let's do the same sort of thing. Let's look at the context, right? So when we read this, we see the word average. So we've guessed that our parameter is going to be mu, right? Average of what? Well, it's the average of the salaries. So that's going to be our variable. And what is the population? Where these salaries live? Where do they come from? And these are salaries from a large company. So our population. So these are the salaries of individuals, and our population is everyone in this particularly large company. And of course, now we can figure out what mu is, right? So mu is the average salary of everyone in the company. And everything should kind of hang together when you're doing this sort of analysis. It should be kind of self-consistent. Average salary of everyone in the company. Okay, good. So now let's try to make sense of the numbers. So we have 22, 5. And we notice that we take a sample of 22 randomly chosen workers. So our n is going to be 22. The average salary in the company was 75K. So notice that this is referencing the whole company. It's not implying that it comes from a sample, right? So this average is a population average. And the same thing applies to the standard deviation. It's from the population. All right. So now we're ready to apply the central limit theorem. So let's look at the assumptions. Do we have a random sample? Check. What about the sample size? Well, our sample size is below 30. So we have to check and see if the salaries have a normal distribution, right? And notice they don't fall into any of these classes, right? And in fact, we know that salaries generally have a right skewed distribution. They're generally not normal. So we don't satisfy the central limit theorem. We don't satisfy the assumptions. We neither have a sample that's large enough or a variable that has a normal distribution. So bottom line, we can't do the problem. Okay. All right, so let's suppose we're going to look at problem 3 now. In fact, I'll just let you read it. You can pause the video. Okay, so let's take a look now at our context. As we're reading the problem, we're seeing the word percentages. So this is suggesting that our parameter here is going to be pi, population percentage. So our variable, right, has to be percentage of something, has to be a percentage of a class. And in this case, we see that 75% of them are empathetic. So the variable here is whether or not a person is empathetic. So it's whether an individual is empathetic. And our population is the collection of all individuals we're interested in. And we can see that that appears to be females. And there's nothing that suggests it's a smaller population, okay? So pi here then must be equal to the percentage of all females that are empathetic. Okay, good. So I want to look at the numbers now and try to make sense of everything. And I notice that I have a 75%. That's one number. 24. Okay, and that seems to be pretty much it. Sample size always has to be in our problem, right? And so sample size is 24. And 75% is a percentage. And the question is, what is it a percentage of? A percentage of a sample or a percentage of a population? And the way that we do that is exactly the same logic as for a quantitative variable. Right? Where is this thing coming from? Is there language that suggests this is coming from a sample, or is it stated as a fact? And therefore it's a parameter. And if we read this, in fact it says, suppose in the population of females, 75% of them are empathetic. So this is actually telling us that the population percentage is in fact 75%. Okay, so now we're ready to use the central limit theorem. So I'm going to go ahead, I'm going to check the assumptions. Notice I have a random sample. It says we take a random sample of 24 women. So the random part is okay. What about the sample size? Is our sample large enough? Well, if it's, in order to be large enough, right, n times pi, which in this case is 24, times 75 is 3/4, right? So 24 times 3/4 has to be greater than or equal to 10. And so if we look at this, right, we're going to see that this goes into 6. We have 18, right? So here, 18 is greater than or equal to 10. So we're okay. But we also have to have n times 1 minus pi greater than 10. So this is going to be 24 times 1/4. And notice this is not true. 6 is not greater than or equal to 10. So our sample is not large enough. So therefore, the answer to our problem is we can't use the central limit theorem because our assumptions are not satisfied. So we can't do the problem. Okay, so our last practice problem here. We take a sample of 100 randomly chosen people in the U.S. and test whether they have the coronavirus. Right now, the percentage in the population isn't quite 12%, but it's predicted to be there relatively shortly. So if the percentage of the population that has a virus is 12%, what distribution will the sample percentages have? And so you can kind of see that here we're working with a percentage, right? So we know that our parameter is pi. Our variable, percentage of what? Percentage of people who have coronavirus. So our variable is whether or not an individual has the coronavirus. And our population are all the people in the U.S. And we can tell that because our sample came from all the people in the U.S. So I'm just kind of going through the context. After a while, you won't write everything out. You'll just kind of do it in your head like this, right? So n is equal to 100. Pi is equal to 12%. And we're ready to test the central limit theorem. So first of all, it is random. Okay. Is our sample large? Is our sample large enough? So I'm testing the assumptions, right? First I test randomness. We're told it's random. Are our assumptions satisfied? Well, 12% times 100 is 12. Okay. And 100 times 88% is going to be 88. So both of those are over 10, so we're okay. Is the sample too large? Well, we have 100 people. There's more than 1,000 people in the U.S., so we're all right. So now we can just state what the distribution of the sample percentages are, right? We automatically can go to that. The sample percentages have a normal distribution, and you can do this using either decimals or percentages. I'm going to do it both ways, okay? So the population parameter is 12, and the standard deviation is going to be pi times 1 minus pi all over 100 square root of. And you can go ahead and you can compute that now. It's not hard to compute. And when you do that, you'll get about so you get 10 about 0.032, somewhere around there. Yeah, it looks good. Okay. Or if I want to express this in terms of percentages, which is generally a little nicer, right? I could convert this to percentages and say pi has a normal distribution centered at 12% with a standard deviation of 3.2%. Either way is fine. When you do the calculations in Excel, though, you're going to have to use decimals, all right? But when you write it, you can leave your answer in terms of percentages. Just make sure that you put the percent sign so people know. All right, so that's pretty much it for understanding what the central limit theorem is actually telling us.